Hello everyone, very welcome to the first session for CLO number 2 of the optimization techniques. Today I will start to discuss about one of the most important methods which can be used for optimization of different processes. The title and as you can see here for this CLO for this and this session and the session which we will have for this week will be about the response surface methodology, as you can see here. But before that, let me introduce myself. My name is Dr. Farza Jalilian Tabar. I'm a senior lecturer of UMP, and also I am serving nowadays for College of Engineering. So as I have started, uh, today topic and this week topic actually is about the response surface methodology. To start this method, I should remind you that it is supposed you have already know about the factorial design, full factorial, fractional factorial, and also you know about the ANOVA analysis, you know about the p-value, you know about the regression analysis, and some other basic fundamental which is required for statistical analysis actually, not only for the optimization, different optimization methods. So I will start this session by this assumption that you already know about that. And I also have checked that in previous video lecture, which was prepared and delivered to you by Dr. Dai, most of these important fundamental are already delivered to you. So I hope you uh, remember them, or at least you can just simply watch the video lecture again to recall them. Okay, first of all, let me tell you what we are going to have for uh, this CLO. First, I will introduce you what is the course requirements for this CLO. What you need to have, what you need to learn actually, and I will start with the history of RSM. I will tell you more about the origin of RSM, the area of the application for this method of optimization. I will also start from factorial design, and I will reach the RSM method. I will tell you the differences and actually why we need to have RSM method, what we why we not use factorial design for all of the experiments, and why we need this RSM method. Actually, RSM method is interesting method. It is actually one of the method to design your experiments, and also you can by this method optimize your process. And finally, we will reach two of the most important design which we have in the RSM, Central Composite Design, or CCD, and Box-Bacon design. I will introduce both of this method to you, and also we will have examples to use to use the software actually, design expert software. I will introduce you and tell you more about that to run these two different design, to design two imaginary examples by design expert software, one of them CCD and the other one which will have the BBD design. First of all, about course requirement, what you need to have actually is software, design expert software. The latest version is version 12. It is a commercial software, so it is not free software. You need to purchase it, you need to pay for that. However, I will put the correct version here, you can use that. for just to practice. However, the academic version also is not free. So the crack version is only option for us for now to use. And I put this software in the Google Class. You can download, and also I have put the installation procedure. So this software, Design Express software, is very important. It is useful also for the factorial design and all of the. It is a software for the, as you can see from its name, actually, it is a software for to design your experiments or DOE. So, but I will just cover and I will teach you how to use this software to design different RSM methods, CCD and ABD. And the book or a textbook which I can introduce you for this CLO for RSM is this book, Response Surface Methodology, which is written by Myers and Montgomery. It is very helpful textbook. However, the number of pages is quite huge and about more than or 800 plus pages uh, we have in this book, but it is really good source to study and to know more about the RSM. I will not go through the details of the book, but this slide, the course which I deliver for RSM, is based on this textbook. So if you need more information, you can refer to this textbook. I think the PDF file is also available on the net, and if you are more interested, you can purchase and buy the hard copy. It is not compulsory, but I just introduced this as a good source for RSM. And the main source for this CLO is the slides, which I will share with you, and also the video lecture, which I deliver recorded one, or we may have face to face. Okay, as I said, you need to know about some basic knowledge actually of the statistics. You need to know about the response variable. You need to know what is factor, what is the level of each factor, which is also a short description of each one of these terms or concepts are also mentioned here. And I will use these words a lot in next slide, and I will actually use the uh, information and knowledge you have learned in the previous session. And we will continue to reach the RSM. First, why this RSM came out? What was the requirement to establish this method? Up to here, you have seen about the factorial design. You know that to run experiments scientifically, you need to define factors, you need to define responses, you may have variables dependent and independent, which are divided to the factors and the responses. And you know about the level of the factors. What was the purpose of that factorial design? When you are interested to see if a variable is effective on the other variable, you need to design an experiment. For example, imagine you are going to see is the temperature effective on the time or duration of the boiling of water, for example. This is an experiment. The temperature is the factor, and response is the time for that boiling process actually. So you need to define a process. If you remember, we had a factor, we had response. And also for factor, we had different levels. So, for example, if you remember, we had uh, mm, the effect of this uh, factor on the responses can be shown like this. For example, imagine we have two level, low, high. Then if this for the temperature, and the response is the boiling time, or the time which is required for boiling, so boiling time. And as you may guess, and according to your experience, by increasing the temperature, the boiling time will reduce. So you remember about this, we call this main effect of the temperature on the boiling time. So by this method, by the factor design, you can see here how is the effect of the temperature on the boiling time. And we had the fractional factorial and two-level factorials and so on, which were useful methods to find this effect. But this is, for the simple models, it works when the factors, the number of factors is not too many. It helps if and also if the level of the factors is not too many. It is also helpful. For example, if we have only low and high, it is okay. So, but if we are interested to check, for example, 0 degrees Celsius, 10 degree, 12, 30, and so on for temperature, you can see here we will have, actually infinity level of the factors, which we can consider their effect on the response. So, how many levels is enough for a, factor to be a study to make sure that we have already have a good model. Actually, if you remember, we had regression model, and we found a correlation between the factor and responses. But the question with that factor design was actually how many levels we can have here. As you can see here, it is infinity. We draw this line, but we imagine it is a linear, changes in the boiling time with a change in the temperature. But usually it may not be like that. For example, if it is like this equation, it is a polynomial. It is, and maybe the change of the temperature, change of the boiling time with temperature is clear according to our experience, but maybe it is not that much clear, this line, the behavior of the curve actually. So the reason which this RSM came out is, as you may guess from its name, RSM is response surface methodology. Later we will see why we call that response surface. Because we now in this method, instead of the levels, we are dealing with the range. We can have a model for whole range here. So here I can just tell you the first thing about the RSM, that we need to have continuous factor actually to use RSM to have the surfaces. So this is one reason which we need RSM. Up to here, up to now, we have already discussed about the modeling, about the design of the experiment by RSM, not optimization. Optimization I will later discuss about that. So here you can see here, instead of different levels, we can have a range by different models. So, however, you have already seen about the regression analysis, we can have different models. for the RSM, for the factorial, and to find the correlation between the factor and responses. You already know about the significant level. So in RSM also, again, we will use those information. RSM was started in the about more middle of the last century, and it was invented by Box and Wilson actually. The initial application for this method was chemical industry. Still, if you go and search for the application area of the RSM, you will find lots of publication or application, real application in the industry for this method in the chemical industry area actually. But nowadays, it is also a popular method for other industries, I can say, or scientific area like product design, uncertainty analysis, even your major, which is mechanical engineering. It can be used also to design your experiments, and we will see some example. I will try to find examples close to the mechanical engineering actually, which is your major. Then, what is objective of RSM? RSM is a collection of mathematical and statistical techniques. As I told you, again, we need those information you have already learned in previous sessions. Mathematics and statistical techniques that are useful for modeling and analysis in application where a response of interest is influenced by several variables and the objective is to optimize the response. So, in other words, simply saying we have some factors. For example, we have a chemical process and we know we have two factors. For example, temperature and time, and the outcome of this process or response is the yield of that process or y. Then we are interested to have the maximum yield of that chemical process by justifying the temperature and time. And we know, according, the initial steps in RSM is more or less same as the factorial design. We need to check if temperature is significantly effective on the uh, yield or the of the process, and also we need to check for time, and also we need to check for the interaction of these two, and also the quadratic values terms of each one of these factors. We need to check all of those them for the response, which are effective on the yield. We call this the modeling. So we will develop models, then we will check the if our model is significant, and finally we will find the temperature and time, which in that temperature and time we have maximum, for example, here in this example, maximum yield of that process. The objective, the final objective of optimization by RSM can be maximization of something or minimizing the response or getting a target actually. Here, for example, we are going to have a maximum yield. So the optimization here is maximizing the yield of that process. We can have also minimizing a process, which be the target of our optimization. For example, we may be interested to minimize the NOx emission of combustion in an internal combustion engine. So also minimization can be an optimization process, or getting to a target to find a specific value. For example, we are interested to have, for those may uh, have information about the engine. For example, we may be interested to keep CO2 emission. As you know, CO2 is not a harmful gas, and it is a product of the combustion, and it is uh, a sign that we have a complete combustion. It is out of the scope of the subject to go to more detail, but the thing you should note is we need to keep CO2 in the optimization process in a target, and we are not interested to reduce it or maximize or minimize it. We are going to reach a target for that. So the optimization process is not always to minimize or maximize something. Sometimes it is getting to a target. And when a nonlinear model is warranted, when there is significant curvature in the response surface, we will see what we mean from uh, this nonlinear model, which we have in RSM. If you remember, in regression, we usually use linear model to find correlation between the response and factors, but here we'll have also nonlinear model. Generally speaking, before I mm, go further, more detail about RSM, let me tell you some applications area or some reason actually which we use RSM. First of all, to determine the factor level that will simultaneously satisfy a set of desired specification. As I told you, these factor levels, I told you about that example temperature. For example, about that process I told you. We have temperature, we have the time. Okay, so in our experiment, which temperature we need to check? How many levels we should select for temperature? Usually it is not that much easy to select. If this is a common question. If you run your experiment and say, okay, I check the process in 20 degrees Celsius and 30 and 40 degrees Celsius, my question will be, why not 5 degrees Celsius? Why not 25 degrees Celsius? Okay, so when we are not sure about the level of the factors, we can use this method, and we will see why we can use this method. The second one is to determine the optimum combination of factors that yield the desired response and describe the response near the optimum. This is optimization process which we do at the last step of the RSM. RSM does not start with optimization. First, we need to have robust model. So the last one is to find a optimum amount or value for the factors to reach a desired response or responses actually. And also, according to the model which we have, you can check how a specific response is affected by changes in the level of the factor or a specified level of the interest. We will see how the factor also change. This is also interesting. You know, when we had that factorial design, we were sure about the point. You know, for each level, for example, uh, we were sure about the amount of the uh, response in that point in factorial design. But we actually, generally, we are not that much uh, confident about the amount of the uh, response in the range between the factors, between the levels of that factor actually. So we can see how the response is affected by changing in the factor. So we can find this line or this polynomial I can say, more confident, and we can be sure, okay, the response will change, and we change in the factor like this, and we can find the uh, response for each amount of the factors, which is also an interesting characteristic. And we use RSM to achieve a quantitative understanding of the system behavior or the region tested. This is more or less similar to previous advantage of the RSM. We can check how exactly it is changing. The response is changing while changing the why we change the factors, or why the factor is changing. And more interesting thing about the RSM is we will replace the complex model. We will see in future slide what I mean from the complex model. Complex models, if you remember, for example, between the response and factor, we need to write an equation, for example, like this, and it may be too complicated and so on. But here in the RSM, we will develop some simple model instead of the complex model, which are a simpler second or are a simple second order regression model, and it is valid within the limited range. So we also use RSM to find the models. In the process of optimization, we will also find the models. I am insisting of the model for RSM because the crucial part in RSM is developing of those models. Optimization is only, I can say, 10% at the last step of the RSM. The models are very important, and we will learn more about the models, how you can check the model which you develop for the RSM, and how you can check their validity, and how you can select the significant terms for the model, and so on. And so the main focus also will be on the modeling part. And here we will reach this question: why it is called response surface? Why we call this response surface methodology? What is the reason for this surface word? Why we call that surface? Let me tell you or explain you the answer to this question with an example. Suppose you are an engineer, you wish to find the levels of temperature X or X1, factor one is temperature, and feed concentration. So we have two factors, temperature and feed concentration, X1 and X2. We are interested to maximize the yield of the process, which these two factors are effective on that process. And also, we know that the yield is a function of the levels of x1 and x2 by this equation. So y as the yield of this process actually is dependent on the level of the x1 and x2, and we have also an intercept for this equation. If you remember from mathematics, we can write this equation like this: e of y equal to f x1 and x2 as our factor. This is our response. So our response is uh, dependent of the factors. And if you notice this, and if you go back to geometry subject, this is the equation which we can find for this function will be equation for a surface like this. In other words, we will have y or response for each combination of x1 and x2. Here you can see that. Let me just show you on this graph. We have time, temperature, hour factor, and here is yield. If if we have only like this, for example, here is yield, here is time. So we will have something like this. For each time, we will have a yield. And also, we for the temperature, we have a correlation between them, and it is like this. Then for the combination of them, we in three-dimensional form, we have yield here, we have time, and temperature here. And you can see here with change, because we already know there is a correlation between the temperature uh, and yield, and also time and yield. So we know by changing the temperature or change in the time, yield also will change. So uh, this in this graph actually, which we use that usually to show the interaction of it, for each temperature and time combination. For example, here the time is like this and temperature, yeah, is like this on this line. For example, temperature is, for example, 10 degrees Celsius and time is 0. Then yield will be like this. And if we change, if we for the time, for example, here and temperature here, we will have another point for the yield. So you can see here, for any combination of time and temperature, we have 1 point. And we already know about that. We can find a model by a regression method, and we can have a regression equation for uh, this, and we will have a line, for example, how these change, for example, for this combination for one level of each one. For example, this is time, then after 20 minutes, and for different temperature. But when time and temperature, both of them is changing, we will have a surface like what you can see here. For example, this line is for this time in different temperature. You can see how yield is changing. Again, this line, each one of this line is one level for the time, and so on. And you can see also in this axis, you can see here, each one of this line is for one level of the temperature, and for different levels of the other factor, which is time. The combination of these for each point, for example, here is for example, here is the time, uh, 77, 18, for example, here is the uh, 29 or 78, for example. So for different temperature. And the combination will give you a surface like this. For each point, it is a combination for time and temperature and the amount of yield. This is a surface, the response surface plot. We have response for a combination of temperature and time. We can also have a counter plot like what you can see here, time, temperature again, and response, amount of the value or amount of yield in each combination of them. For example, here the time is again 78, or let me just find this. Okay, and at this point we have the temperature is much, and as you can see here, we have ISO values as the counters, and you can see here it will be 77. The yield is 77%, for example, in this counter graph. Later we will see more about these counter graphs and also response plot. So these two plots are important, and we will use them in analysis of RSM. Still we haven't touched the discussion about the optimization. We are still in the modeling process, and you can see here why we call this response surface methodology, because here instead of working with the levels, instead of working with the curves like what we had in the regression analysis, and instead of the point or different state, here we have a surface of responses. And you can see here you can see two important things. First of all, here in these graphs, we can only show two factors. So uh, more than two factors for an experiment, we need to use numerical methods to find the surface. So to have these graphs, we need to have two factors. And usually I recommend in your experiment when you are going to use RSM or RSM method actually, it's better to just define two factors, two continuous factors actually, as you can see here, and one response. And so first, you need to have continuous factor. Continuous factor, I think you already know about that, which we can have any values between the levels. And also, we usually it is better to have, we only can use this graph when we have two factors. As I told you, plot, we can always have this plot for two factors. For more than two factors, the optimal yield has to be obtained by numerical optimization, which we will see. And as you can see here, just a hint for you, how will be the process. You can see this surface. This is, you know, the amount of the yield, the value of the yield for each time and temperature. Where is the maximum amount of the yield? Simply by this graph, we can understand. For example, somewhere here will be the maximum amount of the yield for this process. So simply we can, according to this graph, we can understand, for example, for this maximum point, the time is 84 or 85, and the temperature is 177 something. So simply we can find uh, we can optimize the process, and we can find the amount of factors which in those amount we will have the maximum yield. So when you have two factors graphically, you can easily find out and find the optimized point. But usually the graph is not like this. The maximum point is not that much clear. Later we will see different graphs and different type of graphs. So in mouse RSM problems, the form of the relationship between the response and independent variable is unknown. This is an imagination. However, you may know that, for example, by increasing the temperature, the yield will increase. But usually it is not that much clear for us. Maybe we have run a factorial design, but usually we don't know the correlation uh, between the response and factor. Then the first step in RSM is to find a suitable approximation for a true to find a true relationship between y and x. Y is the response and x is the factor. So first we need to find a good approximation between the factors and response. How much will be response by when we have this much of the factor? This is first step of the RSM. And if the response is well modeled by a linear function of independent variables, like what we have here, then the approximating function is the first order model, like what you can see here. I think this equation is, uh, you already know about this equation. It's a regression model, a linear first order model or linear model between the factors, x's, and the response. And if you remember, we could find this model by using 2k or 2k minus p design, the factorial design. If you remember, we could find this equation by those methods. And if we have a curvature in the model, here is our imagination is for the factor. We have this relationship for the factors. Here is the uh, response. Here is the factor. Here is the response. So we imagine the response is changing linearly. We change in the factors. We can use this equation. But if we have a curvature in the system, then a polynomial of higher degree must be used, such as second order model, like, for example, uh, factor response. For example, it will change like this. The response is changing by changing factor like this. The amount of response in each level of the factor will be like this. A polynomial curve, you already know about that by regression analysis actually. And the equation, the second order model for this polynomial can be written like this, which we have coefficient and also for different uh, factors. And if you remember from the regression analysis, this model has a linear interaction and quadratic terms. We have a linear term, uh, interaction term, and we have quadratic term in this model. Simply, this model tell us how response is changing by change in the factors. And if you remember, to know this equation, you need to know about the linear relationship, about or main effect actually. Linear part is checking main effect. Interaction is checking simultaneously for both or more than two factors on the response. And quadratic term also is helpful to find this polynomial curve. Okay, let's see, according to this explanation, how will be a response surface model for two factors. A response surface model for two factors like x1, x2, and a response like y will be like y equal to b0, which is the constant main effect of those two factors, curvature part between those, uh, the level between uh, the level of the factor is actually the point between the level of the factor and interaction, and finally the error. You already know about this model from regression analysis, which we can use this model to find response by for different values of the uh, factors. Actually, in the statistical area or statistic science, usually we just are interested to understand the uh, real phenomenon by the mathematical equation. So here we don't know how is temperature effect on this an imaginary process. For example, you are cooking, okay? Then you don't know how you can make it faster, for example. So you can imagine, okay, if I increase the temperature, um, or increase the temperature, or for the oven, for example, the cooking process will be faster. You know about that. But how about if you use a uh, mm, uh, mm, pressurized cooker? Actually, I forget the name. Pressurized cooker. So it will also again make the process faster. How? By introduction of a new factor, which is the pressure to the model. And to be more specific, we need to have such a model to understand how will be the uh, correlation between the factors, pressure, and the response, the cooking time. You know, to find this equation, what you need to do according to factorial design, you know about that. You need to define level 4 factors and run the experiments. Then you can find a relationship between the factors and responses by this model. We call this modeling. So for two factor, the response surface can be defined by this equation. Then many RSM problems utilize one or both of these approximating polynomials. This one. The response surface analysis is done in terms of the fitted surfaces. You can see here again why we call that response surface, because we are dealing with these surfaces. And also, when you are going to deliver the result of your RSM method, you need to show these surfaces. These surfaces show how the factors, how the response change, we change in the factor. So if we have mm, a smooth surface, usually a second order model is nearly always enough to find that surface. So if the surface is smooth without too many peaks, for example, the surface which we had here, we can call this a smooth surface. If the surface was like this, then it was not that much easy, or more peak, for example, here in the surface, then it was not easy to find a peak for this. And also, it is not that much easy to find an equation to describe that surface. You may know about that from mathematics. But usually, the problem which we are dealing with them also, which are suitable for the RSM, a second order model is enough. Then if the fitted surface is an adequate approximation, higher R square, I hope you already know about this R square because it is also important in the previous session. I think you know about that for the factorial, or especially for the regression analysis, you need to use R square or correlation coefficient, which is important properties of each model. R square is a value between usually we call that 0 and 1, and or negative 1 to 1 actually, as it is more closer to as it is more closer to 1, it means your model is the accuracy of your model is higher. You can predict the factor, the boiling time uh, or cooking time more accurately by knowing the amount of the temperature or factors. So higher R square is desirable, closer to 1 actually. And we have, it can be between negative 1 and 1. However, we are usually interested to find the value between 0 and 1 to show the correlation, the accuracy of the correlation, or the how much is robust the correlation between the response and factors. It can be also in negative side or negative one, which means there is a negative correlation between response and factors. If we have a model with high R square, later also within the software we will see why it is important. Then analysis of the fitted surface will be approximated equivalent to the analysis of the actual surface. So if we don't, first of all, if the surface is smooth, we can have a second order model and it is enough. Then also we need to check the approximation ability of the model, which we use R square. R square closer to 1 is more desirable. It means we can use that equation. Usually R squared higher than 70% or higher than zero point 0.7 is enough to say the model is valid to be used in RSM or optimization process. And this model actually can predict the factors, predict the response by factors almost accurately. And the model is good enough to be used in the optimization process. And according to what I told you, type of the uh, we can have the function which I show you here, the line. This line for different level can be like this. For example, this actually should be like this. We may have this. This is factors. This is the response. These figures means the changing in the response with changing in the factor is linear. There is a linear correlation between the response and factor. We may have also like this, which is a quadratic function, which we can find the response by using the function by quadratic equation. Or maybe it is more complicated and we need to have a cubic function to find the response according to the factors. Here is different level of the factor. So you can see here how it can be complicated. Now, how about if it be more complicated figure, for example, like this, how we can find uh, the correlation between the response and factor. Again, just I repeat, this is helpful equation or graph because, for example, here, if we know, for example, how much is factor, we can guess the amount of response. So this is usefulness of this is advantage of the model. And also here, and also here. But if the correlation between response and factor is too much complicated, how about that? Later we will see how we can deal with them. Now let's see, just consider these uh, different uh, figures. If the response behaves as this figure, it is the linear correlation, the design matrix to quantify that behavior need only contain factors with two levels, low and high. You can guess low, high. This is factor. So simply, if we know 2 points, here we are going to find equation to describe a line. So if you remember from mathematics, we only need 2 points on a line to describe that line, straight line. So if for this 2 points is enough, or two level, here is factor, response, here is factor. So two level here is enough. So this model actually is basic assumption of simple two-level factorial and fractional factorial design, which you have already learned in previous sessions. But if a response behaves as this figure, the minimum number of level required for a factor to quantify the behavior is 3. Again, like this. So we have low factor response. We have high, low, and high amount of the factor. Again, to find, if we have only 2 points, we don't know, and we know it is not linear. We need another curve you know, another level to for the factor, for example, medium, to find this line. Then, according to what we have done for these two condition, you may think, okay, adding the center point to two-level design will satisfy the requirement, but the arrangement of the treatment in the such a matrix can found all quadratic effects which each other. In other words, it will cause to have a more complex model. It will increase the complexity of the model. While a two-level design with center point cannot estimate individual pure quadratic effects, it can detect them effectively. A solution to creating a design matrix. Design matrix, I think it is a uh, phrase which you have already know about that in design factor. We define factors and the level of the factors. So a solution to creating a design matrix, which by using that we can estimate a simple curvature for what we had in figure 1b. This figure is to use three-level factorial design, like what I told you, low, medium, and high. And again, we can, by introduction of three-level, find this uh, line or curve to define response according to the factor. But if we have more complex, like more complex correlation, like what we have here between the response and factor, what about that case? In that case, in more complex cases, such as illustrated in that figure 1.3, the design matrix must contain at least 4 levels of each factor to characterize the behavior of response adequately. Uh, like what this sentence what I read, it is about this figure, means we need 4 for this curve. We need 4 different levels for the factor to find this curve, because I think about it from mathematics. Any changes in the trend of the curve, we need one level to define that change in the curve. So you can see here, according to this process, increase in the number of the uh, levels will increase the number of the coefficient in the equation. Let's go back to this equation. You remember this equation? This is an equation for two factors. And if we have uh, three-level factorial design, I think you remember also. For two factors, the number of combinations which we have in the factorial design is 9, and number of coefficients will be 6. Coefficient means betas which we have here. So here for two factor we have 5. Two factor two level we have 5. For two factor three level we have 9. For three factor we have 27, and you can see here those beta is increasing, and for six factor we will have uh, 729 combinations, possible combinations, and we will have 28 uh, coefficient in that equation. So, and you can see here the number of lines required for 3 power k factorial becomes unacceptable. You can see here, even more quickly than for 2k design. So the last column in this table shows the number of terms present in the quadratic model for each case, which I already uh, told you. So this three-level factorial design, yeah, this three-level also maybe sometimes not be a good design to find this curve. However, even with this three-level factorial design, we have some problem, like what we have here. With only a modest number of factors, the number of run is very large. You can see here. Even an order of magnitude greater than the number of parameters to be estimated when k is not small. So the, the first problem with this three-level factorial design is we have lots of combination. We need to run experiments for many of these treatments. We call them treatments. So the number of the experiment will increase tremendously. For example, here is an example: the absolute minimum number of runs required to estimate all terms present in a four factor. We imagine we have four factors. Quadratic model is 15. So you can see here we need to have at least 15 runs for, here we have only four factor and only uh, we are considering for quadratic model. And same with same procedure when the factors or k is 4, the number of the factor which we have is 4, the required run will be 81 runs. Let me just tell you something here, which is an advantage actually of the response surface methodology, which is the when you have just a few amount of levels for the factors, it is more reasonable to use factorial design. But when you don't know and or the number of levels is high, for example, for time, you are going to check a process during a time or during a range of temperature, and the temperature is important. Each 1 degree Celsius, for example, is important. Between 20 degrees Celsius to 60 degrees Celsius, you have about 40 different levels for each degree Celsius. Then instead of that factorial design, a factor with 40 levels, it is better to use this response surface methodology. So the other advantage of this RSM is we will minimize the required number of runs or experiments to find the correlation between the factors and response, and also to check is the factor effective on the responses or not. So considering a fractional factor at 3 levels is a logical step. Given the success of fractional design applied to 2-level design, you have already know about the fractional design, which is reduce the amount or number of the runs. However, usually it is not a good way to reduce number of runs, because the alias structure for 3-level fractional factorial design is considerably more complex and harder to define than in the 2-level case. So again, we have a problem with the terms which we have in the model for even for this fractional factorial design. So you can see here in this case when we have a complex correlation between the factor and response, the factorial design is not enough design to be used for our experiment. So we need to use another design of experiment, and the matrix of experiment should be designed by the RSM method actually. And here also I can mention about the rotatability. For 3-level factorial design, we don't have rotatability. Usually we don't have rotatability in the design. Later we will see what is rotatability, and we will check and compare the rotatability in the RSM design and also the factorial design. Okay, up to here I think is enough for this session. Next session I will continue to see how this RSM method can, how is the procedure actually, generally how the RSM works, how it reach that peaks. We will start gradually to talk about the optimization. So up to here you have learned and you have seen the differences between factorial design and RSM design and why RSM design is a useful design of experiments to design your experiments actually. The advantages and differences between RSM and factory design was focused. So see you in the next session and discuss more about it.